If you're asked to find the hybridization for F2, that's fluorine gas, we can do that pretty easily by just finding the steric number and looking it up here. So the steric number is the number of sigma bonds and lone pairs. So we have a sigma bond right here. This is a single bond. And then we have one of those plus the lone pairs, 1, 2, 3 lone pairs. So the steric number is 4. That means we have sp3 hybridization. If we looked at the shape of this molecule, we only have 2 atoms, so it's going to be linear with a bond angle of 180 degrees, and we don't really need hybridization to explain it for this molecule. So let's see why we have sp3 hybridization and what that looks like. We'll first write the electron configuration. So fluorine has an atomic number of 9. That means it has 9 protons, and since this is neutral, we have 9 electrons. So we can write an electron configuration of 1s2, 2s2, and then 2p5. So we've used all 9 electrons, and we have the arrangement, the electronic arrangement of those electrons around the nucleus. Let's do an energy diagram based on this. So we'll ignore the 1s because really the 2s, this energy level here, those are the ones involved in the chemical bonding. Those are the ones we use to draw our Lewis structure here. So let's just look at the 2s. In the 2s2, that 2s, we have 2 electrons, and then we have 5 in the p, and the p is split up into these subshells here. We have 1, 2, 3, and then we go back 4, 5 electrons. So this is the unhybridized or ground state for this fluorine here. When fluorine forms the bond, it hybridizes, and we end up with orbitals that are a mix of these 4. Because we have sp3, we're going to mix an s and these 3 p orbitals. And we'll end up with 4 sp3 orbitals, and they're kind of in between here. So you have 1, 2, 4. So you can think of this as an s and 3 p orbitals, this s and these 3 p, mixing together to form a hybrid, which is an average of these 4 orbitals here. So it'll be 25% s character, 75% p. And these are our 2 sp3 orbitals. So we have 2, 4, 6, 7 electrons. Let's fill these up. 1, 2, 3, 4. So this is the hybridized orbitals for the F as it's bonded here. And you can see their energy is kind of in between the 2s and the 2p's here. It's a hybrid, it's a mix. You can also see these 2 here, they represent a lone pair. We have 1, 2, 3 lone pairs, and then we have this 1 electron here, this valence electron, available to form a chemical bond. So when these mix and they hybridize, we end up with these 4 equal orbitals, and they'll look like this here. You can see the big lobe here, and then there's a little lobe over here. So this is where the electron will be found most of the time. So we have 3 lone pairs. Let's put those in. And then we have our 1 electron here, which we said could form a chemical bond. So this is one of the fluorines. And if we bring another fluorine in like this, which will be the same, they're identical, these will overlap. And this will be our chemical bond. This will be our sigma bond right here. And if we look at our Lewis structure, we can see the lone pairs around the F. We can see this bond here, right here between the fluorines. If you were asked to write the notation for this bond here, the hybridization notation, if you're asked to write the notation for this, you could say you have that sigma bond right here, and then it's F2sp3, and then we have the other fluorine here, F2sp3. This is Dr. B with the hybridization of F2 fluorine gas, and thanks for watching.